Previously, we evaluated trigonometric functions of acute angles. Then we evaluated trigonometric functions of angles found on the unit circle. Now we will evaluate trigonometric functions of any angle. It is important to remember that the trig functions are ratios. They are a comparison between two sides of a triangle. The sine, cosine, tangent, secant, cosecant, and cotangent of an angle are calculated by dividing two side lengths of a triangle. The first angles we calculated trigonometric ratios for were acute angles and right triangles. In this diagram, we have an acute angle theta found in a right triangle with side lengths 5, 12, and 13. Because of the location of angle theta, the side measuring 12 units is opposite the angle, while the side measuring 5 units is adjacent to the angle. The hypotenuse measures 13 units. To find the sine of angle theta, we divide the opposite side length by the length of the hypotenuse. The cosine is the adjacent side divided by the hypotenuse, and the tangent is the opposite side divided by the adjacent side. The cosecant is the reciprocal of the sine ratio. The secant is the reciprocal of the cosine of theta, and the cotangent is the reciprocal of the tangent function. All 6 trigonometric functions can be evaluated from an angle when all 3 side lengths of the triangle are known. While the previous method was effective for finding trigonometric ratios of acute angles and right triangles, the unit circle allowed us to find common trig ratios of acute, obtuse, right, straight, angles over 180 degrees, and even negative angles. We can use the coordinates of the points on the circumference of the unit circle to calculate all 6 trig ratios. The sine of the angle is the y-coordinate, the cosine is the x-coordinate, and the tangent of the angle is the y-coordinate divided by the x-coordinate. The cosecant, secant, and cotangent of each angle is the reciprocals of the sine, cosine, and tangent ratios, respectively. Let's use the unit circle to find the values of these trig ratios. To find the sine of 135 degrees, we only need to find 135 degrees on our unit circle, which is right here, and then locate the y-coordinate at that point. And here we have the square root of 2 over 2. So the sine of 135 degrees is simply the square root of 2 over 2. To find the secant of negative 210 degrees, it would be a lot easier if we could find a coterminal angle that is between 0 and 360 degrees, rather than using negative 210 degrees. So first, we will add 360 degrees to 210 degrees to find its coterminal angle. And negative 210 plus 360 equal 150 degrees. So by finding that coterminal angle, the secant of 150 degrees, we will be finding the secant of negative 210 degrees. They will have the same value. Now, secant, we don't know straight off the bat, but we know that secant is the reciprocal of cosine. And the cosine values on the unit circle are the x values, or the x coordinates. And once we find that, we can take the reciprocal and then find the secant. So what is the cosine of 150 degrees? Well, here's 150 degrees here, and our cosine will be negative square root of 3 over 2. Now to find the secant, we need to only find the reciprocal of that. So the secant of 150 degrees will be the reciprocal of negative square root of 3 over 2, which is 2 over the square root of 3. And it really doesn't matter where I put the negative sign. I'll just put the negative sign on the top. I don't like to leave them in the denominator. Okay, we have a couple last things to do. We have a square root symbol in our denominator, so I'm going to rationalize that by multiplying it by the square root of 3 over the square root of 3. That will give me negative 2 times the square root of 3 over 3. And that's a rationalized answer, which is totally great. But now I will highlight our answer by writing it like this. The secant of negative 210 degrees equals negative 2 times the square root of 3 over 3. Now let's try to find all 6 trigonometric ratios for the angle theta that is neither an acute angle in a right triangle nor an angle found on the unit circle. We know the terminal side of this angle passes through the point negative 4, 3. We also know we could potentially use a reference angle to calculate the trig ratios, but we need to find the distance from the origin to the point 4, 3 in order to find all 6 trig ratios. So let's start this off with the diagram. Wow. So here we have our diagram, and we have the point negative 4, 3 that it goes through, and we have our angle theta. Now that obtuse angle is not actually going to help us that much. So instead of using that obtuse angle, why don't we use its reference angle? Now we first use reference angles when we were learning about the unit circle, and it allows you to make an acute right triangle so we can find our side lengths and make our ratios that way. So this is what we're going to do. And now we're going to use this reference angle theta. It's the angle that connects our line or our angle back to the x-axis. If you're in the first quadrant, you don't have to worry about reference angles. But in the second, it will go down to the x-axis. In the third quadrant, it will go up to the x-axis. In the fourth quadrant, it will actually go up to the positive x-axis, which is pretty nice. So this one, I am going to add in a side of this triangle over here. Yep, that one. And that will form a right angle with the base of the triangle, which I could draw in here, down here. Okay, and I know, since I know the coordinate negative 4, 3, I know some of these values. I know that the x value is negative 4, so down here I will write a negative 4, and the y value is 3, so this will be 3. And since I have a right triangle and I have the 2 of the smaller sides, I can use the Pythagorean theorem to calculate the hypotenuse, and then I will have all 3 sides of the triangle, and then it will be very easy to find all 6 trig ratios once we have all 3 sides of the triangle. So over here, you'll notice that the x is negative 4, the y is 3, and I have this r being radius. R is going to be this distance right here, r. If we find that radius of this circle that this 3 point is on, then we'll know how big the hypotenuse of our triangle is. And so it's just the Pythagorean theorem solved up, but instead of a squared plus b squared, it's x squared plus y squared, and the square root, because usually it equals c squared. And to do it all in one step, we'll use the square root. So x is negative 4. And I'll put that in parentheses because we're going to square it. And I want to make sure I square the negative and the 4, not just the 4. And then 3 squared, I don't have to put that in parentheses because there's no signs to worry about. Negative 4 times negative 4 is positive 16. 3 times 3 is 9. 16 plus 9 is 25. And the square root of 25 is 5. So our radius of this circle is going to be 5. Now this r value will always be positive. It just kind of has to be positive. Because even if the individual numbers are negative, we're going to end up squaring them, and then the negatives will go away. So our r will always be positive. But we do have a negative value for x, so some of our signs will be some of our solutions, our fractions, will be negative. Remember, in the first quadrant, everything's positive. In the second quadrant, sine is positive, but cosine and tangent are negative. Third quadrant, tangent is positive, sine and cosine are negative. And in the fourth quadrant, cosine is positive, and sine and tangent are negative. All right, here's the neater version of everything I did. Looks pretty good. So now that we know all three sides of the triangle, just like when we first learned about trig ratios, we have enough information to find all 6 trig ratios. Sine, cosine, and tangent are generally the ones I find first because I have this nice little mnemonic device, SOHCAHTOA, to remind me that sine is the opposite over hypotenuse, cosine is the adjacent over hypotenuse, and tangent is opposite over adjacent. We know what our angle is. Our angle is theta. It is down here. Now we need to mark the diagram, label the sides. So I always label the opposite first, personal preference. So the opposite will be 3. It doesn't come in contact with that angle at all. The adjacent side, well, I'll do the hypotenuse. The hypotenuse is the longest side. It's opposite the right angle. I'll write a little right angle symbol there. That's the hypotenuse. And the adjacent side is the other side. It does come in contact with the angle, and it's not the hypotenuse. Okay, if you remember, sine is opposite over hypotenuse. It's already written up there. Sine is opposite over hypotenuse. So the opposite side is 3, and the hypotenuse is 5. And we don't need to reduce that. We don't need to do anything with that. All 3 sides of this triangle are integer values, so everything is pretty great. Also remember, the sine is going to be positive in this second quadrant, so that looks great. The cosine is the adjacent over hypotenuse. Cosine is adjacent over hypotenuse, so the adjacent is -4, and the hypotenuse is once again 5. Notice that the cosine is negative in this quadrant, and that's good. It's supposed to be. Second quadrant, only sine will be positive. Okay, next we find the tangent. The tangent is opposite over adjacent. The opposite side is 3. The adjacent side is -4. I'm actually just going to move the negative in front. I don't like to leave a negative in the denominator. It gets confusing. But you can put it in front of the fraction, or you can put it in the numerator of the fraction, and that works out a lot better. Now, cosecant, secant, and cotangent are the reciprocals of sine, cosine, and tangent. So since I already have the fractions for sine, cosine, and tangent, the reciprocals should be pretty easy. In fact, the only time that this becomes a problem is when you have square roots in parts of these fractions, because then you might have to rationalize a denominator here or there. But here, the cosecant, if sine is 3/5, the cosecant will be 5 over 3, just the reciprocal. There's no negatives to worry about, so we just leave it like that. The secant is the reciprocal of cosine, so the reciprocal of -4 over 5, I'm going to write it as -5 over 4. Remember that negative could be in the top, it could be in the bottom. Doesn't really matter. I don't like to leave it in the bottom. It gets confusing. And the tangent being -3/4, the cotangent will be, instead of opposite over adjacent, it will be adjacent over opposite, or -4 over 3. And the cosecant, secant, and cotangent follow the same signs that sine, cosine, and tangent do. So if sine's positive, cosecant's going to be positive. If cosine is negative, then secant has to be negative, and if tangent's negative, cotangent has to be negative, because you're using the same numbers to make your ratios. They're just the reciprocals of each other. Once again, this is a neater version of what I just wrote out. So it's time to make this into a much more generalized equation. If I give you a coordinate that an angle passes through, that coordinate will have an x and a y value. And you can use that x and y value to help you find sine, cosine, tangent. It's cosecant, secant, and cotangent. With one exception, we need to know one more piece of information. We need to know the radius of that circle, or the distance from the coordinate I give you to the origin. Now, we didn't need to worry about this with the unit circle because our radius on the unit circle was 1. So the y coordinate, was the sine of that angle because it was y over the radius, 1. So this is kind of an adaptation of the unit of all of the work we did with unit circles. Just adding in that we're probably going to have to calculate a radius length. So with that said, in the unit circle, the sine of theta was just the y coordinate. Now it's going to be the y coordinate divided by r, the length r. Cosine was the x coordinate. Now is the x coordinate divided by r. And tangent, well, tangent's still y divided by x. So that's great. Cosecant and secant are r over y and r over x, respectively. and cotangent is the reciprocal of tangent, so it's x over y. So tangent and cotangent actually have no calculated difference between when we were finding measure of angles on the unit circle and finding these angles that are not on the unit circle. But as long as we can calculate that R value, we can find all of the other ones pretty simply. So let's try a little bit more complicated of a case. Okay, in this problem it says let -7, -5 be a point on the terminal side of theta. Find all 6 trigonometric ratios of theta. Okay, so I have a coordinate, so I have an x and y value, but -7, -5 is not on the unit circle. So I need to calculate my distance from my origin to -7, -5. -7, -5 is in the third quadrant, so I might know, okay, tangent's going to be positive, but sine and cosine are going to be negative. That means cosecant and secant will be negative and cotangent will be positive. That's great, but before we get to that point, let's do the simple part. Let's just find what R is. The equation for R is the square root of x squared plus y squared. And this is just an adaptation of the distance formula or the Pythagorean theorem. So I know my x value is -7 and my y value is -5. I can substitute those. All right, that's great. -7 squared. -7 times -7 is positive 49. -5 times -5 is positive 25. We can take the square root of that, and that will be our R. So our R will equal the square root of 74, which is non-existent. There's no square root of 74, and we can't even simplify it. That's just going to stay as the square root of 74, and that's okay. We can have square roots in trig ratios. We had a bunch of them in the unit circle, so we can keep going with that. This will mean that at some points when we find all 6 ratios, we will have to do some rationalization of denominators. So let's start off with the more generalized one, sine of theta, cosine of theta, and tangent of theta. Okay. Kind of want to change colors here. All right. So the sine of theta, previously we saw that will be y over r. Well, our y is -5. And our r is square root of 74. All right, right off the bat, we've got to rationalize one. That's okay. So we're going to multiply this by the square root of 74 over square root of 74. And I get -5 times the square root of 74 over 74. And I can't even reduce that. But that's the answer. It doesn't have to be pretty. Cosine. All right, here we are with our cosine. Our cosine is our x-coordinate over r. So our x-coordinate is -7, and that's over the square root of 74. All right, we have to rationalize this as well. I'm not going to write square root of 74 over the square root of 74 because we literally just wrote that. But hopefully you notice the pattern. It will be -7 times the square root of 74 over 74. And finally, our tangent. Well, we don't have to worry about square root in the denominator for a tangent because it is y over x, or -5 over -7, which simply reduces to 5 over 7. And once again, it's positive, and that's great because it is in the third quadrant, and tangent is positive there. So it all worked out. Okay, what about the other 3? We have cosecant, which is the reciprocal of sine of theta. Now, don't use our last answer, -5 times the square root of 74 over 74. Actually, go back to what we initially wrote, because we're going to take the reciprocal of it. That will put that square root in the numerator. So cosecant will be square root of 74 over -5. Secant, actually, instead of over -5, Let me erase that. And I will put the negative in the top. The secant of theta is the reciprocal of cosine. I'll go back to what we initially wrote for that before we did the simplification, because we don't need the simplification anymore. And I will write square root of 74, and that's negative, over 7. And finally, cotangent of theta is 5 over 7. The reciprocal of that will be 7 over 5. That one's nice. Okay, this is kind of messy. Let me give you the neater version. Wow, the neater version. Still pretty great. Okay, let's try doing this with a slightly different question type. Okay, here I'm giving you the tangent of theta equals negative 7 over 4. And the cosine of theta is also going to be greater than 0, which means the cosine will end up being positive. And I want to find the sine of theta and the secant of theta. But wait, I didn't get a coordinate here. I didn't get a lot of things. So we are going to have to figure out what our coordinate's going to be, and we're going to have to figure out maybe what the hypotenuse would be, what our R value would be. And they don't give us a lot of information, but they do. We probably could figure out what quadrant this lies in, right? The tangent is negative, the cosine is positive. They had to give us that information for some reason. Okay, let's break this apart. So the tangent of theta is negative 7 over 4. And I know that the top value is a y coordinate and the bottom value is an x coordinate because the tangent of theta is y over x. However, there's that negative sign, and I don't know if it goes with the y coordinate or if it goes with the x coordinate. But this cosine of theta is greater than 0 will help me with that. The tangent is negative, so the tangent is negative in the second and the fourth quadrant, but the cosine is positive. The place where the cosine is positive and the tangent is negative is in the fourth quadrant. So we know we're in the fourth quadrant. We are in x is positive, y is negative. So I just said that. In the fourth quadrant, x is positive, y is negative. So our 4 is going to be positive, and our 7 is going to be negative, because that is what is positive and what is negative in the fourth quadrant. Okay, so now I have my coordinate. Can I find my r? Of course I can. R will equal the square root of x squared, which is 4, plus y squared, which is negative 7. So r equals the square root of 16 plus, and then we have negative 7 squared, which is 49. So r will equal the square root of 65, which looks like we should be able to reduce it, but alas, we can't. So since we have our coordinate and our r value, it should be pretty easy to find, well, especially easy to find sine. Now, if you remember back a couple of minutes, the sine of theta would be y over the r value. And so y is negative 7, and our r value is the square root of 65. So I will rationalize that. And our answer is simply negative 7 times the square root of 65 over 65. Also remember we're in the fourth quadrant, and sine is negative in the fourth quadrant, so our negative value there is good. That's actually a good thing. Cool, now let's work on secant of theta. Now, secant is the reciprocal of cosine. Cosine is x over r, so secant will be r over x. And that will actually work out in our advantage here. Cosine is positive in this, so secant should also be positive. Our r value is the square root of 65. And our x value is 4. And I don't need to do any simplification for once. That's just our answer. Okay, let me clean this up and show you kind of a picture of it. So there we go. We actually kind of, without actually doing the picture out, figured out what quadrant it's in first and kind of drew a picture of it. At least I did in my head. We used the reference angle. We used the point 4, -7 to calculate what r was. That was 65. Or the square root of 65, I should say. And then we used the formulas for sine and secant of trig functions of any angle in order to find sine to be -7 times the square root of 65 over 65, and the secant to be the square root of 65 over 4. Okay, I think it is time that we work on some of these. Let's do it, everybody.